Temperature and thermal expansion are going to be the topic of this first lesson in a chapter on thermal physics, which will cover this topic and then also gases and gas laws. And if that gets a little bit lengthy, I might split that up into 2 additional lessons instead of just 1. But in this lesson, we're going to talk about temperature and temperature scales and then talk about thermal expansion, so the tendency of solids and liquids to expand as they are heated. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So before we can actually introduce the commonly used temperature scales, Celsius, Kelvin, Fahrenheit, we've got to talk about where the basis for temperature even comes from. And it turns out it comes from the Zeroth Law of Thermodynamics. Now, at some point, we're going to talk about the 3 laws of thermodynamics, commonly taught in a chemistry class as well. But they came back and said, well, you know, we really need to define temperature and we need to add a law before those 3 laws. And so they call it the Zeroth Law. So we have the first law of thermodynamics, the second law of thermodynamics, the third law of thermodynamics, and they went back and added the Zeroth Law. And ultimately what that Zeroth Law says is that if 2 objects are in thermal equilibrium, then they're going to be at the same temperature. Now, this idea of thermal equilibrium, well, we know that heat is transferred from typically hotter objects to colder objects if they're in thermal contact. And thermal contact doesn't necessarily mean they're in direct contact, though they could be, and that would be conduction. It could be that a fluid is actually transferring the heat from one to the other, and that fluid could be a gas, and that would be convection. Or it could be that it's actually electromagnetic radiation being the vehicle from which heat is transferred from the hotter to the colder, and that would be radiation. So, but in this case, in any one of those 3, we'll call it thermal contact. And as long as you've got a hotter object and a colder object, which is kind of implying temperature here, I realize, but you're going to have heat transferred from that hotter to the colder. But if they're at exactly the same temperature, one's not hotter than the other, then they're going to be in thermal equilibrium, and there's no net heat transfer between those 2 objects. So here's ultimately what that Zeroth Law said. It says if you have one object in thermal equilibrium with a second object, and that second object's in thermal equilibrium with a third object, well, then the first one must be in thermal equilibrium with a third one. I kind of like to think of it as like the transitive property of thermal equilibrium. But that's ultimately what it said, but the conclusion that we draw from it is that if 2 objects are in thermal equilibrium, they're at the same temperature, and we now have a new word, temperature, that we're defining. So objects in thermal equilibrium are at the same temperature. And they came up with all sorts of early thermometers for measuring this temperature. And that was kind of the foundation for one of the early scales. Now, so if you want to calibrate your thermometer, typically you need to do a 2-point calibration. But what you need is 2 reproducible temperatures that you can use for that calibration. Well, the problem is that, what are you going to use for that? So typically as you add heat to a substance, its temperature goes up, except when you're undergoing a phase change. So it turns out when you're undergoing a phase change, you have 2 phases in equilibrium. So if you're at the freezing point or melting point of water, you have solid and liquid water together in equilibrium. And if you're adding heat to that system, it turns out the temperature doesn't change, it just melts the ice. And once all the ice is melted, if you keep adding heat, then the temperature will start going up. But as long as you have those 2 phases in equilibrium, you can add all the heat you want, and you'll change the proportion of the 2 phases, but you won't change the temperature. And so now we have these stable calibration points as long as you're using the phase change points. And so the common ones used were the melting point or freezing point of water and then the boiling point of water. And along came Anders Celsius, and he said, hey, let's take that calibration point and I'm going to call that 0 on my scale. And then I'm going to take the boiling point and I'm going to call that 100, and we'll just break up the difference into 100 individual degree units. And so today we call this 100 degrees, 0 degrees Celsius and 100 degrees Celsius. So in Mr. Anders Celsius's day, they called it centigrade. But in the 1950s, they changed it to honor his name, so to speak. But you might still hear centigrade used a time or 2, but Celsius is more common these days. But that's where that scale comes from. But we have a problem with this scale, is that this 0 is not a real 0. And it's not the biggest deal in the world, but it does kind of give some misconceptions on occasion. So let's, for example, say that, I've got, this marker right here that's 4 inches long. And if I had one that was 8 inches long, you could say, well, the one that's 8 inches long is twice as long as the one that's 4 inches long, and that would totally be true. But let's just pretend for a minute that I define a new scale. I decide that I'm the center of the universe, and that 5'8" is the new 0 for height scale. Okay, So, and I tell you that I've got a friend who's 4 inches tall on this new Chad scale, and I've got another friend who's 8 inches tall on the new Chad scale. Well, is my friend who's 8 inches tall on the Chad scale actually twice the height of my other friend who's 4 inches tall on the Chad scale? Well, no, because again, if 5'8" is the new 0, then 4 inches tall corresponds to 6 foot, and 8 inches would correspond to 6'4". And if you're 6'4", you're definitely not twice as tall as somebody who's 6 foot. And so the problem is that my height, 5'8", is not a real 0. And so that's the issue. And so same thing here. This is not a real 0 for temperature. You can get colder than 0 degrees Celsius and have negative temperatures on the Celsius scale. And so if I said, let's compare 30 degrees Celsius and 60 degrees Celsius, if you said, well, 60 degrees Celsius is double the temperature of 30 degrees Celsius, it's not true because we're not dealing with a scale that has a real 0. Well, they came up with a scale that had a real 0, and if you take a look here, so if we take a plot of pressure versus temperature, so using what was called a constant volume thermometer. So it turns out you could get your calibration points of, let's do that right here, at 0 degrees Celsius and 100 degrees Celsius. And it turns out if you use these constant volume thermometers, which had a constant volume of a gas inside, so you could alter that pressure of that gas and you'd still hit these lovely calibration points at the same point. So you'd hit it right there through those 2 points. That's a really terrible line. I'm sorry about that, but it is the way it works. We'll kind of go back here, extrapolate that back. But let's say we measured it at a slightly different pressure and you get the same 2 points. Then we did it at a slightly elevated pressure. So, and you get 2 points. And the temperatures were the same, 0 degrees Celsius and 100 degrees Celsius all the time, but in starting at a different pressure, so it's your pressures that are going to be a little bit different when you measure those temperatures. Well, the interesting thing is that when they extrapolated it back on these straight lines, they all met at a common point right down here when the pressure would be theoretically 0, the lowest possible pressure. There's technically no such thing as a negative pressure. When somebody uses the term negative pressure, they just mean it's lower than whatever they're comparing it to, but there's no such thing as actual negative pressure. All right, so this was kind of an interesting thing, and it turns out with these constant volume thermometers, it didn't matter even which gas they put in them. They would all converge at this same common point, which just happened to be negative 273.15 degrees Celsius. Well, this is, again, the lowest theoretical pressure, and so what they said is that that's converging at the lowest possible temperature that could exist as well. It's a real 0. And so they created a new scale. They called that point absolute 0. So way over here on this new scale, and they called it Kelvin. So that was 0 Kelvin. And that corresponded on the Celsius scale to negative 273.15 degrees Celsius, which means that 0 degrees Celsius now corresponded to 273.15 Kelvin. So they did something nice here. So even though the 0 point is different, the distance between each degree was exactly the same as the Celsius scale. And so if you go up 100 degrees to the boiling point of water, then you go up 100 on the Kelvin scale to 373.15 Kelvin. Cool, so not a bad scale, and it has a real 0. And so if instead of comparing 30 degrees Celsius to 60 degrees Celsius, so, which is not a double in temperature, but if you compare 30 Kelvin to 60 Kelvin, that is a doubling of the temperature because we now have a real 0 for our scale. Okay, so when you're converting between Celsius and Kelvin, the real question just is, are you adding 273 or subtracting 273? And technically 273.15, but a lot of you probably will just end up rounding it to the nearest whole number is my guess. But leave that at the discretion of your professor. So if I told you I have 20 degrees Celsius. So, well, 20 degrees Celsius, that's right in here somewhere. And so on the Kelvin scale, it's going to be between 273 and 373 Kelvin. So in this case, all you got to do is add 273. So I need to find out that that's going to correspond on our Kelvin scale to 293.15 Kelvin. And so when you're converting from Celsius to Kelvin, you add 273. Well, what if we started with that backwards? And I said, well, what if I've got 293.15 Kelvin? And I said, what is that in Celsius? Well, now you'd need to subtract off the 273.15 and get the 20 degrees Celsius out of that. Cool. So whether you add or subtract, you simply got to memorize. All right, so now we got the problem, and the problem is the redheaded stepchild scale called the Fahrenheit scale. which isn't too commonly used except in the US. When you get the weather in the US, it's going to be in Fahrenheit, and that is no small nuisance to international students who come here. And so I happen to live in Arizona, where it gets ridiculously hot in the summer. So when a student asks me, how hot is it in the middle of August? And I say it's 115 degrees, they just look at me and I have to specify it's 115 degrees Fahrenheit. So because 115 degrees on the scale they're used to in Celsius would be a little bit crazy. But still, when I say 150 degrees, they're like, well, I gotta convert that to figure out what that actually means. And so that's an issue. And so you gotta know how to convert between Fahrenheit and Celsius, which is a little more of a pain in the butt because the distance between degrees on the Celsius and Fahrenheit scales is not the same. And I'm really sorry they're not. But you're either gonna have to memorize an equation or you're gonna have to be able to derive that equation, which is what I typically do, FYI, and I'm gonna show you how to do that. All right, so you gotta be able to know at least 2 points to create the line between the Fahrenheit and the Celsius scale. And so it turns out the freezing point of water on the Fahrenheit scale, that's 32 degrees Fahrenheit. And there's many a student who actually knows this connection right here. Now on the boiling point, they might know this one, they might not. It's 212 degrees Fahrenheit for the boiling point of water. And if you got these 2 points, so on the 2 different scales, you can set up the straight line between them and get the whole y equals mx plus b, and life is good. So what's nice though is that a lot of students forget this one. And so there's one other point that I like to use, and that is minus 40 degrees Celsius, because that just so conveniently happens to correspond to minus 40 degrees Fahrenheit. It's the point where the 2 scales converge, if you will. So same on both scales at minus 40 and only at minus 40. All right, so let's derive this equation between Fahrenheit and Celsius. So we'll plot Celsius on the x-axis, we'll plot Fahrenheit on the y-axis, and we'll come up with our scale here. So in this case, we're gonna create a point, say right here, and that's gonna correspond to 0 on the Celsius scale, but 32 Fahrenheit on the Fahrenheit scale. All right, so that's this point here, the freezing point of water. We'll go to the boiling point of water here, and so we'd have to go over to 100 degrees Celsius, but way up to 212 on the Fahrenheit scale. So that's 100 degrees Celsius and 212 Fahrenheit. But if we extrapolated this back somewhere back over here, maybe about that ballpark, we'd get negative 40 degrees Celsius and negative 40 degrees Fahrenheit on that same line. So now let's derive that line from any 2 of those points. And again, I typically will use these 2. But you could use these 2 or even the 2 extremes. As long as you got 2 points, you can define the line there. And we'll get the slope-intercept form of that line. So y equals mx plus b. In this case, on the y-axis, that's where the degrees Fahrenheit is. So that'll equal the slope. And on the x-axis, that's where the degrees Celsius are. And then plus b. In this case, we might more properly write this as TF equals our slope times TC plus b, and do it that way. All right, so in this case, with again, Fahrenheit on the y-axis and Celsius on the x-axis, we can see our y-intercept right there where it crossed the y-axis. It's right at 32 Fahrenheit here. So our y-intercept here is just gonna be that plus 32. But we need that slope, and if you recall, slope is rise over 1, or delta y over delta x, which is y2 minus y1 over x2 minus x1. And so in this case, let's say we did it from these 2 points here, from 32 to 212. Well, 212 minus 32 is 180. So, and then here for the run, 100 minus 0 is 100. Well, 180 over 100 reduces down to 9 over 5. And so there's your conversion from Celsius to Fahrenheit. You just plug the Celsius temperature in right there, and this equation spits out the Fahrenheit. Now notice, you could have picked any 2 of these points. And again, these are the 2 that I typically remember right off the top of my head. And so if you go from there, the rise would be from negative 40 to 32, and 32 minus a negative 40, so 32 plus 40 would be 72 for the rise. And then the run from negative 40 to 0, well, 0 again minus a negative 40 is 0 plus 40, which is 40. And 72 over 40, once again, is going to reduce down to 9 over 5 when you divide by 8. So any 2 of those points is going to get you this lovely equation right here. Now, if you want to go the other way, this is going to get you from Celsius to Fahrenheit. Well, what if you want to get from Fahrenheit to Celsius? So then you just rearrange this to solve for the Celsius instead. So first thing we'll do is subtract from 32 here. So I'll have TF minus 32 is going to equal 9 over 5 times TC. But if we want to solve for TC, then we need to multiply the entire other side of the equation by the reciprocal, by 5/9. And that's where the equation comes from in going from Fahrenheit to Celsius. So if my international friends get here in August and I say, it's 115 degrees Fahrenheit, and they're like, well, what is that in Celsius? Well, first thing I'll do is I'll take 115, I'll subtract off 32 and get 83, and then I'll multiply that by 5 over 9. So times 5 over 9, and we get 46.111 degrees Celsius, which is pretty hot for most of the international students I've talked to. All right, so that is our scales here. Let's do a little bit of a calculation. Now, and I realize we've done a calculation, but let's do the one that's on the study guide here. All right, so if you thought 115 Fahrenheit was hot, question says, the hottest recorded temperature on Earth is 56.7 degrees Celsius. Question is, express this in Kelvin and Fahrenheit. So if we see 56.7 here, on the Kelvin scale, I can see that, oh, it's going to be somewhere between 273 and 373. On the Fahrenheit scale, it's going to have to be somewhere between 32 and 212. So I could ballpark it potentially. So, but to actually do the conversion, well, to get to the Kelvin scale here, we got the temperature in Kelvin is going to equal the temperature in Celsius plus 273. And so in this case, we'll just take that 56.7 plus 273. And in Kelvin we'll get, and technically we'll make that 273.15, be as exact as we can. Some of your professors will want that from you. All right, so 56.7 plus 273.15, it's going to get us 329.85, but we only had 3 sig figs in the original temperature. We should express this in only 3 sig figs, so 329.85 is going to round up to 330, but we have a problem there, right? So that's 330 Kelvin, but that's only got 2 sig figs. So either put the line over it, which again, I personally hate to do, or I'll write this in scientific notation and make this 3.30 times 10 to the 1 2 Kelvin. Okay, so now what if we want to convert this into Fahrenheit? Now, if you've got the equation handy, obviously just use the equation. If you've got to derive it, great. But one thing you should realize, again, is that 56.7 degrees Celsius should be somewhere in the ballpark of like 120, 130, somewhere in that range on the Fahrenheit scale, just ballparking it in between the freezing point and boiling point of water. So in this case, to go from Celsius to Fahrenheit, we got Fahrenheit equals, in this case, the 5 over 9. Oh, I've got that backwards. Let's try that again. How about the 9 over 5? All right, so we can plug that 56.7 right in. Let our calculator do the work for us. All right, so 56.7 times 9 over 5 plus 32. It's going to get us 134.06. In 3 sig figs, I'll round down to 134 degrees Fahrenheit. So now we'll briefly talk about thermal expansion of solids and liquids, and we'll not talk about gases in this section. So it turns out that gases are much more compressible and therefore much more subject to greater expansion than solids or liquids, and we'll deal with those separately when we deal with like gas laws and stuff. So, but for thermal expansion of solids and liquids, we have some simple equations we can follow for linear expansion, area expansion, and volume expansion. And it turns out we've got a couple things to define here. So L naught, A naught, and V naught are the original length, original area, or the original volume of the object you're looking at. So, and then delta T is just simply the change in temperature on the Celsius scale. So because these coefficients up here, these are called the coefficient of linear expansion, the coefficient of area expansion, or the coefficient of volume expansion. So these are all typically given in units of per degree Celsius, which means then that temperature change needs to be in degrees Celsius. Now here's the deal though. Well, if it's a temperature change, because the spacing in between degrees is the same on the Celsius and the Kelvin scale. If you calculated that delta T change in temperature on either scale, it'd come out the same. Now on the Fahrenheit scale, though, it would come out different. So be careful not to calculate it in the Fahrenheit scale. All right, so if you take a look at these coefficients here, so the coefficient of linear expansion is related to the coefficient of area expansion and volume expansion. So this one right here, gamma, is actually equal to 2 times alpha. So, and beta here is equal to 3 times alpha. So, and the way this works is that when you're talking about area, well, you're talking about 2 dimensions, not just 1 dimension like we were with the linear equation up top. And so with 2 dimensions, it turns out if you actually work it out, so one thing to know, all of these are approximations. So, but when you actually work out the derivation, you find out that you get a factor of 2 times that coefficient of linear expansion here for 2 dimensions. And then for volume, you get 3 times that coefficient of linear expansion for 3 dimensions. And so here beta is equal to 3 times that alpha. Now for a lot of you, you may actually have all 3 of these omitted from your course. So, and then some of you even still might only see the first one with linear expansion and might not see the second 2. And then some of you might see all 3. Well, obviously I'm just covering all 3 to cover my bases. So, but if any of this is omitted from your course, then by all means ignore. But from here, it typically is going to be simple plug and chug. So, and the question on the handout we're going to do here says, what is the change in the length of a 0.50 meter long aluminum rod when its temperature is raised from 22 degrees Celsius to 62 degrees Celsius? And then the coefficient of linear expansion for aluminum is given as 2.4 times 10 to the minus 5 per degree Celsius. Second question says, what % increase in length is this? So 2 parts to this question. All right, so it's just simply going to be a plug and chug here. So we've got delta L equals alpha L naught times the change in temperature. So a couple things you should see from this equation. So the bigger the temperature change, the bigger the expansion. So the change in length is proportional to that temperature change. So if you double the temperature change, you should double the expansion. Now, technically, these coefficients are themselves not constant. So as long as you use them over a small enough temperature range, you can use the typical average values that are provided. But typically, if you get big temperature changes over a wide range, all of a sudden now this might get a little more complicated because you might actually end up using calculus to solve this if you were an engineer or something like that. So because these themselves are functions of temperature. But not something you're going to see in your physics class here, at least in your freshman physics class. And so in this case, if we want to calculate this change in length, first thing we need is that coefficient given as 2.4 times 10 to the minus 5. When I say per degree Celsius, you could also write that as Celsius to the minus 1, which is what we did here, times the original length, which was given as 0.50 meters for that aluminum rod, and then times the change in temperature. And going from 22 Celsius to 62 Celsius, final minus initial, 62 minus 22, is a delta T of 40 degrees Celsius. So, and if you look at your units here, so your per degree Celsius here and your degree Celsius here cancel, and your change in length comes out in meters, just like it should. We'll let our calculator do the work here for us. So 2.4 times 10 to the negative 5 times 0.5 and times 40 gets us 4.8 times 10 to the negative 4. And that's in meters. So we want 2 sig figs to go with the original length we were given. That's got 2 sig figs, so life is good. Second question is, what % increase in length is this? So in that case, we're really wanting delta L over L naught times 100, which in this case is that 4.8 times 10 to the minus 4, all over 0.50 meters times 100. And you can pretty well ballpark this in your head. If you notice that 4.8 times 10 to the minus 4 is approximately the same as 0.00, so 3 zeros and then a 5 if I round the 4.8 up to 5. And so in this case, 0.0005 over 0.5 and then times 100, and you can figure out this is somewhere right around 0.1%. But again, we'll let our calculator do the heavy lifting for us. All right, so last answer, 4.8 times 10 minus 4 divided by 0.5 and times 100 comes out to 0.096%. Cool. And any calculations you might do for area or volume changes would be directly analogous. If you have found this lesson helpful, consider giving it a like. Happy studying.